good morning or good whatever, everybody. For us, it's the afternoon in Europe. So welcome to the third day of the quantum algorithms in number theory meeting. And the first speaker will be András Gilyén. So András got his PhD from the University of Amsterdam in 2019 under the supervision of Ronald de Wolf and Harry Burnham. He was then an IQIM postdoctoral fellow at Caltech. Received some prizes, and then he was also a Google Research Fellow in Berkeley, and now is currently in Hungary in the Alfréd Rényi Institute of Mathematics. And so he will speak on a very hot topic these days related to quantum algorithms and linear algebra. András, you have the floor.
Thank you for the kind introduction. Yes, I will talk about quantum algorithms and mostly how we can view many quantum algorithms through the lenses of linear algebra. And I will start the talk by reviewing some results about quantum walks. For two reasons, quantum walks are used a lot in applications related to like cryptography and related fields. And also there were like historically early development was around quantum walks, and later the tools that we learned during this time as a community became generalized in several means and led to a more general framework of many quantum algorithms later. So quantum walks, at least the discrete time quantum walks, were invented as a way to somehow mimic a classical random walk on a graph, on a weighted graph, in a way that we can connect what we see in this quantum walk to what we see in the classical walk, but it still should have some edge over classical algorithms. So it's useful to review how a discrete time random walk works on a weighted graph. If we have a graph on vertex set V with edges E, and we have some non-negative edge weights W, then we can define the transition probability in one step as with transition to V from U with weight with probability, which is the weight of this edge W VU divided by all the edge weights going out from this vertex U. So really, if we are at any vertex U, we transition to a neighboring vertex according to the edge weights that we see around us. And clearly, it will be a Markov process if we define it this way. And so we can describe this Markov process with a stochastic matrix P, and this transition probability is just the VU matrix element of this Markov chain matrix, this transition matrix. And if we want to perform a random walk on an object, a graph, or something, then well, we can break down the task of implementing such a walk to three simple primitives. And usually in these applications, we will be concerned about finding some vertex set in a clever way. And so we assume that there is a set of marked vertices denoted by M. To start the random walk, we will sample an initial vertex according to some distribution sigma. And so we need to be able to, this is the setup cost, to sample the initial vertex. Then there is the update when we are given at a given vertex U, and we want to sample V with the transition probabilities PVU. So this is to do one step, and the checking step is that we should be able to check whether the given vertex where we are at is marked or not. And if we have these primitives, then we can just sample initial vertex and then in every subsequent step, just update and check and iterate this until we find the marked vertex. Now we would like to define a quantum walk, which is resembling this classical walk. And for this, we introduce primitives that are somehow making the same thing, just in a quantum way. So the setup will be replaced by an operation, which from some fixed initial state or zero state, say, it prepares a superposition over the vertices with the amplitude square root sigma v, so that if we would measure this this quantum state after applying this operation, we would see a vertex v with probability sigma v. So it really mimics it is really a generalization of the classical setup operation. And we also would like to do some update operation when we have two registers. The first register is again set to some default value, say the 0. The second register is at the vertex u. And we want to be able to transition this vertex v with probability puv, so pvu. And then therefore we want to prepare the state which keeps the last register, the u vertex where we were, and prepares a superposition over the neighboring vertices with the correct amplitude. So again, if we would measure the first register, we would see a neighboring vertex with the appropriate probability. It is again generalizing the classical update step. And while the checking step is again just it computes the indicator function of the marked vertices, again on a fixed register that we set to 0 initially. So these are quite logical generalizations of these 3 individual steps that I showed you for the classical walks. And it turns out that given these simple primitives, we can actually indeed define a quantum walk, which is usually called the Szegedy quantum walk, which in some way acts similarly or analogously to the classical random walk. And this operator, the walk operator W, will be an interesting combination of these update operations. Turns out that if we apply the update and swap the 2 registers where these 2 vertices are stored in the update, and then do the inverse of this update operator, this dagger sign is the complex, this is the adjoint, the complex adjoint. And well, because it's a unitary matrix, this update operator, this is just inverse as well. This is a physicist notation. I hope that it's not very disturbing. Anyway, so if we apply this u swap and u inverse, then this is again a unitary operation. And how it relates to the classical random walk, that if we look at this unitary matrix, but focus on the top left corner, which is the dimension just matches. So if it's an n vertex walk, then it will be an n by n matrix, and this top left corner of this unitary matrix will be just exactly the stochastic matrix that we define in the classical random walk. And so this is why it shows why it's a good way to define this unitary sequence and this quantum walk operator this way, because really it has a direct connection to the classical walk. And I will soon tell a bit more about why it's advantageous to have this in this unitary form rather than this stochastic matrix. And maybe this is best explained by quantum fast forwarding, which was a very nice insight into the inner workings of these quantum walks. This is a result due to Apers and Sarlette from 2018. So they showed that cleverly using these quantum walk operators that I showed you, you can implement an operator V. This is a quantum circuit. It has the property that now the top left corner will be not the original stochastic matrix P, but its Tth power. So in a way, it relates to a T-step Markov chain, and maybe it's an approximation to some small error epsilon. And the interesting thing that we can achieve this quantum analog of this t-step walk, classical walk, using only roughly square root of t uses of the quantum walk operators. That includes this update and check operators. And the proof of this is really just a polynomial identity, which states that we can approximate this monomial, which is actually 2t. This would be just basically 2t step of this classical random walk. So imagine that as opposed to this single variable x, we can put here this Markov chain matrix, and we approximated this with a linear combination of Chebyshev polynomials of the variable x or the variable p. And why is this useful? Because as you can see, we approximate a roughly a degree 2t polynomial with polynomials that are of degree only roughly square root of t. And this is useful because it turns out that these Chebyshev polynomials, these just naturally appear when we iterate this quantum walk operator. If we just iterate this quantum walk operator with some additional reflection within every step, then these unitary circuits will have just a Chebyshev polynomial applied to this Markov chain matrix, and that will be in the top left corner of this big unitary that appears. So in a way, iterating the quantum walk operator k times applies a degree k Chebyshev polynomial to this transition matrix, which appears in the top left corner of this big unitary matrix that we have at hand. So and then this linear combination of unitaries technique, it tells you that once you have a bunch of matrices, now these are all polynomial functions of this original Markov chain matrix, then you can take linear combinations of those within a quantum circuit, and that is an easy construction. I don't want to like put here the details because it's not important. The important message is that once you have some matrices, you can take linear combinations whenever the one norm of the coefficients is at most one, and this is the case for this particle decomposition. Actually, this trick is used in also classical algorithms, that somehow iterating a matrix t times can be achieved by basically only iterating it roughly square root of t times, just cleverly like combining different steps. So it is related also to the power method and the Lanczos method, if you are familiar with that. This trick happens in many classical computer science topics, and here it just plays hand in hand with the quantum formalism, and somehow intuitively explains why we get a quadratic speedup in the quantum setting. We can somehow emulate a t-step classical walk by only using roughly square root of t resources. And so this was a very nice and intuitive explanation why we have a quadratic advantage in this quantum setting, which I summarize in this slide. So what are the advantages of this Szegedy quantum walk-based search when we have some marked vertex set M? Well, to analyze, to state the advantage, it's useful to examine the hitting time, which is the expected time to hit a marked vertex starting from a stationary distribution of this Markov chain. And so if in the setup we use the stationary distribution, which is denoted by pi here, so we prepare the corresponding superposition of the vertices, then first Szegedy showed in 2004, when he invented this quantum walk, that you can actually detect the presence of marked vertices, i.e. you can show that this marked set is like not empty in time which is quadratically smaller than the classical heating time. And then later this result was extended in some special cases to also being able to find the marked vertex in a quadratic, in some sense quadratically quicker time by Manier, Nayak, Roland, and Chanta in 2006. And up to some polylogarithmic factors, this was basically then improved to full generality in 2019, where now we can, for any kind of Markov chain elevated graph, we can find a marked vertex in roughly square root of the heating time of the classical walk. So this really shows you that you have basically a quadratic advantage compared to classical search methods using the same Markov structure or graph structure. And somehow I wanted to like tell you the intuition behind, which is coming from this fast forwarding insight. Actually, the proof of this more general result also builds on some of the insights from this fast forwarding. And so these results are nice, but they are requiring you to start from the stationary distribution of this Markov chain, which is might not be always available to you. So there are other extensions where you can start from an arbitrary distribution, and correspondingly, the improvement that you get is expressed in terms of the commute time, which is the expected time to start from a vertex, visit a marked vertex, and return to an unmarked vertex where you started from, roughly. Well, it depends on the exact setting, but something, intuitively speaking, something like this. And so Bellows showed, again, detection was easier. In 2013, Bellows showed that you can detect marked vertices with square root of the heating time using this another modification of these quantum walks. And now again in 2019, this was extended to being able to find a marked vertex in general, again in roughly square root of the commute time. It was like two papers that had a fairly different approach, but came to the same conclusion. Yes, so these are the general results about quadratic improvements in discrete time quantum walks. And already earlier versions of these results were sufficient to handle and treat many interesting problems. And most of the applications actually consider a specific graph called Johnson graph, where you have some base set M, and the vertices of this Johnson graph are subsets of this base set, so that of a fixed size. So it would be all the size k subsets of M, that would be the vertices, and the edges are between subsets that differ in only 2 elements. So that is the Johnson graph. And it turns out that many problems can be cast as a walk on the Johnson graph. For example, the most important example, which actually was the motivation to define the Szegedy quantum walks, is the element distinctness problem, studied by Ambainis in 2013. So here, the question is, when we have a black box that computes a function on inputs some n elements, the question is whether there are 2 different elements so that the function evaluates the same value on I and j. So I and j are 2 distinct elements that have the same function value, and we would like to decide if there is such a pair and also find such a collision or such a pair if there exists. And actually, interesting thing is that the tight lower bound was first found by Aronson and Shi in 2001, and then Ambainis' quantum walk algorithm showed a matching upper bound of n to the 2/3, which is clearly an improvement. Classically, you basically need to like read essentially all all function values, so you can't do better than n, whereas n to the 2/3 is an optimal query complexity in this case, and that is basically a quantum walk on the Johnson graph. And there are other related problems where these techniques were applied. For example, element distinctness, triangle finding, where actually the best algorithm today is not quantum walk based algorithm, but maybe the second best algorithm is based on a quantum walk on the Johnson graph. And then, well, we basically have a adjacency oracle for the graph. We can ask for any pairs of vertices, whether they have an edge or not, and the question is whether there is a triangle in this graph. And the query complexity of this using this quantum walk algorithm of Monte Carlo and Szegedy is n to the 13/10, which was later improved by Lego slightly. And another example is matrix product verification, when we have black boxes that tell the entries of n by n matrices A, B, or C, and the question is whether A, B equals C hold, and these are over some finite fields, these matrices, and the query complexity is n to the 5/3 at most, as by this quantum walk based algorithm of Burman and Spalek in 2004. So already these quantum walk algorithms cover lots of interesting problems by themselves, including k-distinctness, and later I will see you how they further generalize. Yeah, but before that, I think it's also relevant for crypto purposes. So let me spend one more slide on the k-distinctness problem. And the question is whether there are k-distinct elements that are mapped to the same image. So it's a generalization of the element distinctness problem. And Ambainis gave a Johnson graph-based quantum walk algorithm, which has query complexity n to the k over k+1. And this was improved for the case of three distinctness based on these more elaborate quantum walks that I mentioned by Bellows, and that was an n to the 5/7 algorithm in 2013. And further improvements for general K were developed by Bellows, but that's a kind of complicated algorithm and not based on quantum walks. And we know what's the query complexity of those algorithms, but those algorithms are not necessarily efficient. So the actual implementation cost might be much higher. It's still an open problem to understand their actual gate complexity of these learning graph-based algorithms. And yeah, here I should mention that people also studies in this direction some time and space trade-offs for these problems, and the recent result of Hamoudi and Monte made some progress towards the conjecture, the lower bound, where it's conjectured that the query time squared times the space, this product is at least n squared. Still, yes. Okay, so this much about quantum walks directly. And now I would like to explain a bit how these quantum walk algorithms and this perspective that I introduced on them can be generalized to more general linear algebra type algorithms and problems. So here a key concept is block encoding, which is a way to represent the large matrices on a quantum computer efficiently. And well, the quantum circuits that are the programs on a quantum computer, essentially, those are described by unitary matrices. However, we often want to work with non-unitary matrices, and as long as a matrix A has spectral norm at most 1, then we can actually find a unitary matrix where this A matrix is the top left corner. So we will represent matrices at the top left corner of unitary matrices, and I can write this pictorially as like this matrix where the top left corner is A, or I can just say that A equals this all zero states, some all zero state tensor identity, and so U sandwiched with it, and again some all zero states and the identity. And that is just a different way of saying that the top left corner of U is A. This is just notation. And this is a very generic way of looking at these matrix constructions. The good thing is that many matrices can be represented in such a block encoding efficiently. While a trivial example is that if I have an efficiently implementable unitary U, then it is just a block encoding of itself. It's a trivial example. The less trivial one is if we have a sparse matrix with efficiently computable matrix elements, then we can also represent that in a quantum circuit, the block encoding. And there are examples that are maybe a bit more far-fetched. So for example, matrix stored in some clever data structure in a quantum RAM that can be also represented as a block encoding, and some physically motivated examples also occur, like a density operator, which we have a recipe to prepare. We can also represent the density operator as a block encoding, and also some measurement operators. If we can perform the measurement operators, then we can represent the measurement operator itself as a block encoding. These are a bit more physics motivated examples, so I don't want to delve too much on them. I just want to illustrate that there are many different ways of getting block encodings of various matrices. And the good thing is that once we have these building blocks, these matrices, we can actually combine them nicely. So I already mentioned this linear combination of unitaries lemma, which basically says that if we have block encodings of matrices HA, then we can implement convex combinations of these matrices efficiently, and it's a small modification of the original circuits. And if we have block encodings of matrix A and B, then we can also implement the block encoding of A times B, which is not much more difficult than just basically applying the two quantum circuits after each other. There is a little bit of carefulness needed to actually have the A times B product appearing, but it is not difficult, and you can get that. And you can not only get a matrix product this way, but you can also get tensor product very similar way. So yeah, in a quantum world, once you represent matrices as block encodings, you have a very versatile toolbox to form linear combinations, state products, and so on. And a generalization of this Szegedy quantum walk operators is this quantum singularity transformation that we proved with Low and Wiebe 2018. And I told you that if we just repeat this Szegedy quantum walk operator, then somehow Chebyshev polynomials of this matrix appear. And Chebyshev polynomials are nice, so it's a very useful observation in itself. But it turns out that a much more broad class of polynomial transformations can be efficiently executed on these block encodings. And so the precise statement is the following. If you have a polynomial map which maps the interval -1, 1 to -1, 1, and it's a degree polynomial which is odd, that means that only the odd degree coefficients are non-zero, and we have a block encoding of a matrix A. While this matrix A can be always written in terms of a singular value decomposition with sum over I, sigma I singular values, and Wi, Vi singular vectors. So take your polynomial map, which is bounded and odd degree and odd, and consider any block-encoded matrix and its single value decomposition, then we have a quantum circuit that now represents a matrix which is similar looking, but where the singular values are transformed by this polynomial, while the singular vectors remain the same. And this quantum circuit really has a very common structure, and they are a sequence of angles that is efficiently computable and only depends on the polynomial itself that we want to represent. And so this is the quantum circuit. We have the block encoding of unitary U and its inverse. We repeat these in a sequence d times, and between each application of U and U dagger, we do some, this is some like controlled operations, where the control is on as many ancilla qubits as many are required for the block encoding, and there is a single qubit rotation happening on an ancilla qubit. And there is some Hadamard gate applied to this qubit at the very beginning and the very end. And this circuit just turns out to transform the singular vectors of the block encoding as I stated. And the nice thing is that whenever your polynomial satisfies the conditions, namely that it's bounded, maps -1, 1 to -1, 1, degree d and odd, then you can always find these angles, and depending on which polynomial you want to apply to your singular values, just choose the angles accordingly, and while the quantum computing or quantum mechanics will just do the job for you. So this is a nice generalization of Szegedy quantum walks. Basically, in Szegedy quantum walks, these angles, I think all the angles are pi-half. If all the angles are pi-half, then the polynomial transformation just becomes this Chebyshev polynomial, and now we extended it to all sorts of bounded polynomials. Okay, so this is a somewhat abstract result, and I don't know, maybe if you have some questions at this point, it's useful to clarify them. Well, if not, then I continue. And yeah, I should mention here that similar result holds for even polynomials as well. Okay, one application of this theorem is fixed point amplitude amplification. This application was one of the motivation which led to these generalizations. This was considered in this form by Yoder, and Chuang in 2014. And so the amplitude amplification is the following. It's a story of the good, the bad, and the unitary, because you have a unitary matrix that again acts on some fixed initial state, prepares with probability p a good state, and it marks the good state with a 0 ancilla qubit, and with probability 1 minus p, it will prepare a bad state, but it flags with the first qubit that it actually didn't succeed and prepared the bad state. And so this is what we have. So this is some operation that with some probability prepares the state that we wish, and with some probability it fails. And well, the goal is to get this good state and get rid of the bad part. So in a matrix form, what we know is that well, the O0 state that just basically picks out the first column of this unitary U, and what we know that the good part is marked with a 0 qubit, the bad part is marked with 1. So basically the first half of the first column is this matrix is the good state subnormalized with square root p. And so this is the unitary that we have at hand, and we would like to fix this unitary in a way that it will only prepare the good state for us and never the bad state. the O0 input. This is what we want to achieve. And so if I put it in these words, then we can basically say that this unitary, the initial unitary that probabilistically prepares the good state, is a block encoding of this funny matrix, which is essentially a column vector. And so I can just apply this quantum singular value transformation to this matrix, which is block encoding this column matrix, this column vector. And so here the singular value corresponding to this column vector will be just square root of p. So what I essentially want to do, I want to transform this square root of p to 1. And that means that I transform this singular value, which was the square root of the success probability, to 1, meaning that I always succeed or almost always succeed. And well, for this, I can just find a polynomial approximation of this step function, which from 0 steps up to 1, so that at square root p it already is extremely close to 1. So this is success probability is almost 1. And here, well, you might wonder, why don't I just choose the constant 1 polynomial? That surely works, but that's not an odd polynomial. So yeah, for this thing to work, I need an odd polynomial. In this case, it turns out, and an odd polynomial, in particular in 0, must take the value 0. So it really must. I must find a polynomial that approximates this jump very, very well, and then jumps to almost 1 at square root p or anything above that. Okay, so now that we translated this fixed point amplitude amplification to this matrix language, it is essentially immediate how you solve it. It turns out that you can find an epsilon approximate step function like here in this green curve, which has degree about log 1 over epsilon over square root p. And ultimately, it means that you can prepare the solved state with about 1 over square root p repetitions of your circuit, which is better than classical. Classically, you would need 1 over p repetitions until success. Yeah. Okay, so that was actually finding this good state. But similarly, if we don't really care about preparing a state, just want to estimate the probability of something happening, we have a similar situation, but now we just want to distinguish whether this probability of getting the good state, is it like less than or equal than p minus delta or p plus delta for some fixed p. That is a valid question that we can ask, and we can distinguish these two cases. We have this delta margin essentially, and again, we apply the same trick. Now we just need a approximating function which doesn't step up at 0 but at this square root p value, and again we can solve this distinguishing problem using such a polynomial, and the degree of the polynomial is similarly log 1 over epsilon over delta. So the complexity of distinguishing these two cases, how many times we need to quantum sample from this sampler to distinguish the two probabilities, is something like 1 over delta, which is better than classical, because classically you would need basically 1 over delta squared to achieve such precision in estimating this probability. And more generally, we can speed up Monte Carlo methods, as pointed out by Montanaro in 2015, quadratically. And to state this, suppose that we have a sampling algorithm that samples from a random variable x. And well, in Monte Carlo estimation, we would like to estimate this expectation value of this random variable, say with epsilon precision. And we can do this essentially using sigma square over epsilon square samples, where sigma square is the variance and epsilon is the precision with which we want to estimate this expectation value. And it turns out in a quantum setting, when we can sample in a quantum by some quantum means from this random variable, we can estimate this expectation value with only sigma over epsilon samples. So again, we get a quadratic improvement here. This is a general story in this Markov in this Monte Carlo estimation setting. And what we need for this, on top of so what is a stronger requirement in this setting compared to classical, that we need to be able to implement this sampler as a quantum circuit. And there are some tricks how you get to this complexity, but they are very similar to what I already showed you in the previous slides. Okay, so now I want to move to a slightly different type of application to these linear algebra problems, and that is the quantum linear equation solving or HHL algorithm. And so here we want to basically invert the matrix, or well, inversion maybe not always possible, but the pseudo-inverse always exists, so that at least we can always define. And so in this problem, we have AX equals B, an equation, and we know B and we know A and want to find X. But we want to solve this problem in a quantum way, so that actually we want to output a quantum state X, which is proportional to the solution that we would define as the A plus B. So A plus is the pseudo-inverse of A applied to the vector B, which is again a quantum state. So this would be solving this linear equation in a quantum sense. And well, it turns out again that it's a very simple consequence of this singularity transformation that I told you. Because if the matrix A has, well, it has always some singular decomposition. If I take that, one can see that the pseudo-inverse of A is just a singular value transformation of the adjoint matrix. So if I take the adjoint of A, then the left and right singular vectors swap places, but the singular value remains the same. The pseudo-inverse, we don't only swap the order of the left and right singular vectors, but we also invert the singular value. And that is what we will do using some polynomial approximation, using this quantum singular value transformation. However, there is an obvious problem here, that the 1 over x function that is not a polynomial and very far from being bounded, that's a diverging function. So in order to be able to solve this problem, we need to make some assumptions that we have some region where the non-zero singular values are banned. And if I have this region, which is denoted by red here, where I have no singular values, then I can just find a polynomial that approximates the 1 over x function very well outside this region. And in this forbidden region where I don't have any singular value anyway, I just, the polynomial acts arbitrarily, but remains bounded. And if one puts together all these details that are required here, turns out that the complexity of this problem is something like sparsity times the condition number of the matrix. And this condition number is related to like the width of this region where we assume that there are no singular values. And well, also there is some time t coming from the assumptions of the input. So in time t, we can prepare the input state p, which is the right-hand side of the equation, and find and compute the non-zero elements in a row and or column of A in this matrix. If we have this, then up to some polynomial logarithmic terms, the complexity will be T times the sparsity times the condition number of the matrix, which is a very tantalizing result. It seems like we get an exponential speed up in terms of the matrix size for solving linear equation systems. And since linear equation systems are everywhere, it seems like this is a super important application of quantum algorithms with a potential of many exponential speedups. However, because of the solution is only happening in a quantum way, it's difficult to find applications where all these fine print can be resolved. And there was a very interesting application suggested by Chen Gao for finding the solution of quadratic polynomial systems, and I try to showcase you the difficulties and the consequences of this quantum algorithm. So they proposed to solve this problem using this HHL algorithm. And so what they did, they said that let's convert this quadratic polynomial equation system to a much larger equation, which is only a linear equation system, and solve that using HHL algorithm. It will be an exponential sized equation system, but that is not a huge problem for the quantum algorithm, so that's no problem. And how they do this is that they fix some degree d larger than the max degree of all these polynomials, and and take all the monomials that have degree at most d, and add some trivial constraints to this polynomial constraints that you already have, that will essentially, so the quadratic polynomials are over Z2, but here the HHL algorithm works over C, so we somehow need to enforce the field equations and essentially we'll force these variables to be either 0 or 1, which could be in principle any complex number because of the assumptions of HHL, but we will force them to be 0 or 1 by adding these trivial constraints that xi squared minus xi equals 0. And well, one needs to be also a bit careful about dealing with the modulo 2 freedom by adding some additional constraints, but this can be all engineered properly. And then the next step in the construction of this so-called Macaulay matrix from these polynomials is that for every constraint, we will take a multiple of the constraint itself and all these monomials of this bounded degree and add them as new equations, while original equations were true. So when we multiply them with a monomial, both left and right hand side, of course, the new equations will be also true. But if we do this with enough monomials to a high enough degree, then actually after this operation is done, we can just treat each monomial as a new variable and solve this highly nonlinear equation system, which is highly redundant as a linear equation now, treating all these monomials as independent linear variables. So this is basically the Macaulay matrix approach to solve these quadratic polynomial systems. And it seems that this is a very good match for the HHL algorithm. So there are some very good news here that if we choose this D large enough, then there is a unique solution over the complex numbers, and that corresponds to the original Boolean solution of the system. And the vector B that is on the right hand side of the equation that will have at most C non-zero elements, where C was the number of original equations, because when we multiply an equation with a monomial, a non-trivial monomial, then it will have no constant term at all. So only the original equations give rise to the constant terms, which are essentially the right hand side of the equation system. So B will be like very sparse and easy to prepare because we exactly know which are the few non-zero constant terms. And it also turns out that the solution in this regime, when there is a unique solution and there is a one-to-one correspondence, then the solution vector will be just an indicator of the monomials. So recall that this vector x will have coordinates that corresponds to monomials, and it will be essentially an indicator of the monomials that evaluate to 1 for the unique Boolean solution. So really, once we have this quantum state, by a few measurements, it's easy to extract which are the Boolean variables that should be one in the unique solution. So it looks like super nice match to this difficult to satisfy HHL algorithm. But then there are some bad news which were unclear for a while. Namely, it was unclear if the condition number behaves nicely or not, or maybe it behaves nicely for some systems, and then for some system, for those systems, this is a good approach to solve it using quantum algorithm. But the bad news is actually that the solution vector, we know exactly the structure. It will be this indicator function, as I told you, and we can just compute its norm. And the condition number can be actually lower bounded by the ratio of this vector x and the vector b. And well, I don't think I have time to explain these computations in detail, but it turns out that because of this structure of the solution vector, condition number will be always as large that that some brute force classical algorithms with some slight, maybe some with some like Grover search or some easy quantum algorithm beat this approach every time. And while we tried to improve a little bit on this application, and we made some progress, but it still seems that in general this will probably not give you exponential speedups, despite this very nice structure in the problem. It seems that this condition number is really an issue that we don't know how to avoid yet. Anyway, this was for a few years unknown if this is how big of a threat this HHL algorithm for these multivariate systems. But recently we concluded that probably it's not a big threat because of this argument, which is a recent paper by Ding, Giorgio, Hallgren, Lee, and myself. Okay, so this maybe like shows you both the potential and the difficulty of using the HHL algorithm for such real problems. And well, I don't really have much more time left. I just have like 2 more slides, a bit of an overview for different algorithmic techniques, just to have maybe I'm just quickly telling what these are about. So I just wanted to say that there are different branches of algorithms that I didn't cover, but are somewhat related regarding to optimization. For example, if we have an unstructured optimization problem, we can find an optimal element in square root of the number of elements. This is related to Grover search and is known as the Dürr-Hoyer algorithm. And in discrete structures, there are other optimization problems, like Dijkstra's algorithm can be improved by applying clever places, Grover search and related things, and for matching and flow problems. So optimization has interesting potential to be sped up by quantum algorithms, and this is also true for some NP-hard problems, like speeding up the finding solution of 3 set and speedups for backtracking algorithms, and also more recently polynomial speedups for dynamic programming algorithms for various difficult problems. And another direction is continuous optimization as opposed to discrete optimization, where we have a solution like speedups based on this linear equation solving or regression, like this HH algorithm that I showed you. But there are also speedups for solving linear programs and semi-definite programs. And more recently, people started looking into speeding up quantum interpolation methods. And there are some other bit more abstract results about exponential speedups in some convex optimization settings. Yes, and there are some statistical stochastic estimation problems where we can get speedups, quadratic speedups for Monte Carlo type problems, some distribution testing problems, and estimating entropies or estimating the histogram. And yeah, so these are, if you have any more questions, I really didn't have time to explain this more. Just I wanted to give a little bit of an outlook towards different type of techniques of my talk, and so I think I will leave a little bit of room for questions as well.
Okay, thank you for